In this video, we discuss simple matrix multiplication in CUDA, a continuation of our introduction to CUDA programming. The diagram here shows the multiplication of matrix A to matrix B, okay? And we get matrix C. Okay? So to get an element of C, we just find the dot product of a row vector of A and the corresponding column vector of B. Here, like the element C12 is given by A11 times B12 plus A12 times B22. Okay, and this is the general formula for any ij element of C. It is given by the sum from k equals 1 to n, okay, and aik times bkj. Okay, sum of this gives us the Cij element. Okay. And in general, if A is of rank m by n, like here it is 4 by 2, okay, 4 rows, 2 columns, okay, and B is n, okay, times L, n equals 2, L equals 3, then the result will be m times L. Like here, the result will be 4 times 3, 4 rows, okay, 3 columns. Okay. And now let's see how we can implement matrix multiplication in CUDA. To start, we first consider a simple C program. We consider the simple M and L 4, 3, 4. M and L are the values we discuss here. Okay. And here's the implementation of the dot product. Okay. We just pass in pointers. Okay. That means we consider the elements to be arranged in sequence, in linear order. Okay. So the dot product, okay, basically is the sum, okay, of the product of these elements. Okay. So the sum is given by the sum plus A. Now this is in two-dimensional aik, but in one dimension it is I times m plus k. Okay. And then for B, bkj, okay, is in one dimension is k times L plus j. Okay. And for C, Cij in two dimension, in one dimension is Ci times L plus j. Okay, so L is this L. Okay, and here the sum is from 0 to n minus 1. We start from 0 instead of starting from 1. Okay. And we just consider a simple example. We'll print out the matrices to check. Okay, this function is to print out a matrix, okay, with n rows and n columns. Okay. So we declare the matrix A to be these values, 4 times 3, and then the B to be 3 times 4, okay, and then C will be ML in 2 dimensions, or 4 times 4. Okay. And we just iterate through the rows and columns, okay, to find all the dot products. Okay, we pass in ij and the pointers to A and pointers to B and pointers to C. Okay, so the values are returned in C, okay, as you can see. Okay, and then we print out the matrices for checking. Okay, now let's copy this and have a quick check. So copy this, and here's empty. Suppose we call this mate ul.cpp. So we paste this. Okay, so get this. save it. Now we compile it here. So we just save this. So we say G++ and then minus O, the output, to be made the mistype. Okay, it's with G++. Okay, so you can see that when we execute, okay, we have this A times B, we get these values, okay, which is correct. Okay, so this is the C++ for matrix multiplication. Now, just we can copy this to this. Okay, main1.cu as the starting point of the CUDA program. Okay. In the CUDA program, we just need to make minor modifications. Okay. Again, we need to add this keyword, say global. Okay. The dot product. Okay. So we add this. Okay. This keyword for a CUDA function, which is also referred to as a kernel. Okay. And as we discussed before, we need to declare, say, pointers to the GPU memory that hold the data. Okay. And the array will be of the same size as the arrays in the main memory. So it is use sizeof to calculate the sizes of the matrices. Okay, and then use CUDA malloc to allocate memory, okay, in the GPU memory. And then we copy the data to the GPU memory using this command, CUDA mem cpy, okay, CUDA mem host to device. Okay. And then we just call the function. We use one block and one thread. Okay. So all these are the same as C++. Okay. And then at the end we copy this back. Okay. And we free the memory. So it's pretty straightforward. So we copy this to our program. So we paste it here. So we did this twice, so we delete this. And so we could delete this, the same as this. So here we use one block, one thread to do all the dot products. Okay. So again, we have to iterate through all the elements of C. Okay. And again, we print out the result. Okay. So now let's save this. Okay. And we compile it. So we use this. And we CC the NVIDIA compiler. Okay. -1 U -O 1. And let's execute it. 1. So again, we get the result. Okay, same result. That's correct. Okay. So it is pretty straightforward for this one. Oh, Oh, sorry, I forgot to add this. Okay, actually we should add these statements at the end. Okay, so here we should add this. And we compile again. So again, no error. Okay, so it is correct. Okay. So that's our first matrix multiplication in CUDA. Okay. And now suppose we consider higher dimension. Okay. So suppose M is 32, N is 30, L is 32. And now we don't want to print out all the elements. Which, as a demo, we consider all the elements in A and B as square root 2, which is equal to this value. Okay. So that means the product of two elements will give us 2. Okay. And so the value of an element in C would be 2 times, say, N, that's 60 here. Okay. So we just want to vary a routine. Instead of checking, print out all the elements, we check the error. Okay. If, say, the element minus 2 times N is larger than the maximum error, okay, then we have error. Okay. Otherwise, okay, it is correct. Okay. We print out just the first element, okay, so there won't be a mess. Okay. So let's copy this again. And we copy this 1.cu to 2, okay, cu. So we change all this. Okay. We could remove those spaces. Okay. So that's what we have. And for the main, so we change our AB elements. So in the AB, we just initialize all elements to square root 2. Okay. So we copy this. I think we used to do it here. And we don't need this here because we declared that here already. Okay. And check error, we do that after we have done the calculation and transfer the data back, and we don't want to print out all the elements. It will be a mess. And then we free the device memory. Okay. So that's our program. Okay. And now let's compile it. Okay. So this is 2. Okay. And you can see that, okay, so the result is correct, okay, passed, okay. Say the first element is 60, okay. And actually all the elements in C should be 60. Now here we have only used one thread to do the calculation. If you look at this using MV Pro, you can see that okay, has to call the routine 1024 times, okay, so the total time used will be this amount, okay. And we can speed this up using multi-thread to do the calculations, okay. As we discussed before, for a CUDA GPU, okay, at the physical level, 32 threads are bundled as a thread swap, and all the threads execute the same statement at any time, except when branching. Okay. At the logical level, a block contains one or more threads, and a grid contains one or more blocks. Okay. So the threads are organized into blocks, okay, and blocks are organized into threads. Okay. So this diagram shows the blocks and threads. Okay. So this is a grid. It contains of different blocks. Okay. And each block, okay, starting from block 0, block 1, okay, is labeled by two indices. Okay. You can say that is x, y. Okay. So this is x, this is y. The first is y, the second is x, or you can say it column and row. Okay. And so the dimension of this grid, okay, in the x direction, 1, 2, 3, 4, it is 4. Okay. And in the y direction, it is 1, 2, 3 is 3. So there's grid dim.y is 3, dim.x is 4. Okay. And for when we refer to a particular block, okay, then we can specify using the x, y parameters. Okay. Like this block, block 1, 2, okay, the block idx dot x, okay, is 2, okay, the column number, and dot y is 1, okay, the row number. Okay. And within this block, suppose we consider block 1, 2, okay, it contains a lot of threads, okay, organized in the 3 dimensions. Okay. Again, in this dimension, the columns, it is x. So x you have 1, 2, 3, 4, 5, 5. So the block dimension in x is 5, and the block dimension in y is 1, 2, 3, 4, 4. Okay, and the block dimension in C is 1, 2, 3, 3. Okay, and when we refer to a thread within this block, okay, we use the XYZ parameter to specify it. Okay, so here, okay, is the front front array. Okay, so the Z is 0. Okay, and you can see that it is in the 0, 1, 2. Okay, is row 2. Okay, so column 2. Okay, so the y is 2. Okay, and then the 0, 1 is row 1. So dot x is 1. Okay, so thread idx dot x is 1, idx dot y is 2, and dot z is 0. So this two dimension can be mapped nicely to a two-dimensional array or a matrix. Okay. So by now we can use one thread to handle one summation. Okay. Then we can speed up the process. Okay. So suppose we only use one block. Okay, one block only. To simplify it first. Okay, just one block without using another block. So one block threads. Okay, so in this case, okay, the row I, okay, will be thread idx.x. Okay, or the in this direction, the row. Okay, and the column is given for our thread idx.x. Okay, in this direction. Okay, the row. Then x. Okay. So that's ij. So we do the same summation. Okay. Say aij is given by this. Sorry, aik. Okay, it's I times n plus k times bkj is bk times l plus j. Okay, and then the c element. Okay, I times l plus j. Okay. So this is carried out by one thread. And of course, the thread still need to do this summation. Okay. Yeah, you could further speed it out by using a technique called tiled matrix multiplication. Okay. But we are not discussing that at this point. And here, okay, instead of using 1, 1, okay, we pass in the blocks per grid and threads per block. Okay, as we just mentioned, we just use one block. Okay, so blocks per grid is 1. Okay, and threads per block is ml. Okay, so we pass in these parameters so that this could be extracted from here. Okay, so but at this point we just use one block, one grid. Okay, so we could modify a program to this. So we don't need to pass in ij. Suppose we call this free. Okay. So product. Okay, becomes this. Actually, we find a better name would be modify, because we find the dot products of all the C elements. So we don't need this anymore. And here we use only one block. So we don't need this for loops. Okay, so it'll be like this. And we also have the check error. And then now let's compile that. That will be 3. 3. So again, it passed, okay. But now here you can compare. Before. So it takes that much time, iterating through 10, 24 times with 5 milliseconds, but now this one, so you can see that I only need to go for once, and so it is 15 microseconds, okay, instead of say milliseconds. Okay, like this one, okay, milliseconds. Okay. So it is much faster. Okay. Now suppose we have higher dimensions. Okay. Then in that case, we may need to use more than one block. Okay. So suppose we consider M and L to be like that, and the maximum number of threads that block can handle is only 32 times 32, depending on your GPU. Okay. Newer GPU may handle more. Okay. So then in this case, we need to use more than one block, because one block of thread, okay, are not sufficient to handle all the elements. So suppose we multiply this, copy this to may4.cu. Okay. So here we have larger constants. So in this case, if the number of blocks that we need is larger than this, then we need to change the block size to the maximum for the 2. And then we need to have more than one block. Okay, blocks per grid will be equal to the ceiling function L divided by the 2. Okay, and in the y direction it is M divided by 32. So we need to add this statement to our program. Okay. So we have to add this here. Is this the right program? Double check. Yeah. Okay. So if M times L, okay, the number of elements in C is larger than the number of threads that a block will hold, then we need more than one block. Okay. And it is calculated by these two formulas. The ceiling function of L divided by 32 and ceiling function M divided by 32. Okay. And here we need to modify this. Because one block is not enough. IJ will extend to another block, so we need to modify to this, like this, okay, to extend it to the other block, okay, by using the block dimension. Okay. So this will be our IJ. Okay, others won't be changed. Now let's compile this. Oh, sorry. This will be NVCC. And again, we got the correct result. Okay? So this is the program. The only thing changes here. Okay, we have to extend to the next block. Okay, after the current block is used up. Okay, so like in the diagram here. Okay, so we at the beginning we just use 0, 0. But when we finish using all these blocks, all these threads in here, we extend to this one. Okay, and then this one, and so on. Okay, so this is how it works, and we can check the profile. So again, only one call we just need. Okay. Okay, so this is a discussion of simple matrix multiplication in CUDA. Okay, it's very simple. Okay, and some values are hard coded. Of course, you could always modify this and apply it and modify it to your own applications. Yeah. Well, yeah. Thank you for watching. If you think that this video is helpful to you, please give it a like. Thank you.